Yes, a plenum-rated power cable with the standard color code does exist. The National Electrical Code Section 725.156 permits the use of power cables rated for 600 volts in plenums, provided they are installed in approved raceways. These raceways can include conduit and wireways. Listed and labeled cables meeting these requirements are readily available from various manufacturers. For example, Southwire offers a 14 American wire gauge, 3-conductor power cable with part number 121,230,014 that is plenum rated and adheres to the standard color code of brown, blue, and green with yellow stripe. It is not necessary to purchase plenum cables and then attempt to tape the conductor ends to achieve the desired color coding. Employing a listed and labeled cable that inherently meets the necessary requirements constitutes the safest and most dependable approach. Here are some other options for plenum-rated cables with the standard color code. Firstly, Belden cable 9518X, a 14 American wire gauge 3-conductor CMP cable with brown, blue, and green with yellow stripes. Secondly, General cable 40,437, a 14 American wire gauge 3-conductor CMP cable with brown, blue, and green with yellow stripe. And thirdly, Prysmian 1483, a 14 American wire gauge 3-conductor CMP cable with brown, blue, and green with yellow stripe. When selecting electrical cables for installation in plenums, it is crucial to adhere to the regulations and guidelines set forth in the National Electrical Code, (NEC). Plenums are defined as spaces within a building that are used for the circulation of environmental air, such as heating, ventilation, and air conditioning or HVAC systems. These spaces often include drop ceilings, raised floors, and other concealed areas. Due to the potential for fire and smoke to spread rapidly through plenums, special requirements are in place to ensure the safety of building occupants. The NEC addresses wiring methods for electrical systems in Chapter 3, Wiring Methods and Materials. Section 300.22 specifically covers wiring in ducts, plenums, and other spaces used for environmental air. This section mandates that only wiring methods specifically listed and labeled for use in environmental air spaces are permitted. This is to minimize the risk of fire propagation and the release of toxic fumes in the event of a fire. Cables that are suitable for use in plenums are typically designated as CMP, which stands for Communications Multipurpose Plenum. CMP cables are constructed with materials that exhibit low smoke and flame characteristics, meaning they produce minimal smoke and do not readily propagate flame. This helps to reduce the risk of smoke inhalation and allows occupants more time to evacuate the building in the event of a fire. In addition to CMP cables, other wiring methods that are permitted in plenums include metal conduit, such as electrical metallic tubing or IMT, and rigid metal conduit or RMC, as well as flexible metal conduit or FMC with certain restrictions. These wiring methods provide a physical barrier to protect the conductors from damage and help to contain any fire that may occur. When selecting electrical cables and wiring methods for plenum installations, it is essential to verify that they are listed and labeled by a nationally recognized testing laboratory, such as Underwriters Laboratories, or ALL, or Intertech, or et al. Listing and labeling indicate that the products have been tested and certified to meet the applicable safety standards. The National Electrical Code Section 725.156, referred to previously, specifically addresses the use of power cables in Class 2 and Class 3 circuits. Class 2 and Class 3 circuits are low-energy circuits that are commonly used for control, signaling, and communication applications. Section 725.156 permits the use of 600-volt power cables in Class 2 and Class 3 circuits, provided that they are installed in approved raceways. This means that the power cables must be installed in metal conduit such as EMT or RMC, or in other approved raceways such as wireways or cable trays. The raceway provides a physical barrier to protect the conductors from damage and helps to contain any fire that may occur. It is important to note that the requirements for wiring in plenums can vary depending on the specific application and the local building codes. Always consult with a qualified electrical engineer or inspector to ensure that the installation complies with all applicable regulations. The standard color code for power conductors in North America is typically brown, orange, and yellow for the 3 phases of a 480-volt system, and black, red, and blue for the 3 phases of a 208-volt or 240-volt system. The neutral conductor is typically white or gray, and the equipment grounding conductor is typically green or green with a yellow stripe. However, in some applications, it may be necessary to use a different color code. For example, in some industrial facilities, a different color code may be used to identify different voltage levels or different types of equipment. In these cases, it is important to clearly document the color code and ensure that all personnel are aware of the color code. When selecting electrical cables, it is important to choose cables that are rated for the appropriate voltage and current. The voltage rating of a cable indicates the maximum voltage that the cable can safely withstand. The current rating of a cable indicates the maximum current that the cable can safely carry. It is important to choose cables that are rated for the highest voltage and current that they will be exposed to in the application. It is also important to consider the ambient temperature when selecting electrical cables. The ambient temperature is the temperature of the environment in which the cable will be installed. Cables are typically rated for a maximum ambient temperature. If the ambient temperature exceeds the cable's rating, the cable may overheat and fail. When installing electrical cables, it is important to follow all applicable codes and standards. The NEC provides detailed instructions for the installation of electrical cables. It is important to follow these instructions carefully to ensure that the installation is safe and reliable. Some additional factors to consider when selecting and installing electrical cables. Firstly, the type of insulation. The insulation of a cable protects the conductors from damage and prevents electrical shorts. There are many different types of insulation available, each with its own advantages and disadvantages. Secondly, the size of the conductors. The size of the conductors in a cable determines the amount of current that the cable can safely carry. It is important to choose a cable with conductors that are large enough to handle the expected current. Thirdly, the flexibility of the cable. The flexibility of a cable is important in applications where the cable will be bent or moved. Flexible cables are easier to install and are less likely to be damaged by bending. Fourthly, the resistance to chemicals. If the cable will be exposed to chemicals, it is important to choose a cable that is resistant to those chemicals. Fifthly, the resistance to abrasion. If the cable will be exposed to abrasion, it is important to choose a cable that is resistant to abrasion. Sixthly, the cost of the cable. The cost of electrical cables can vary widely depending on the type of cable, the size of the conductors, and the other features. It is important to consider the cost of the cable when making a selection, but it is also important to choose a cable that is suitable for the application. To elaborate further on the National Electrical Code, or NEC, and its relevance to electrical installations, it is essential to understand its structure and purpose. The NEC is a comprehensive set of standards and guidelines that govern the safe installation of electrical wiring and equipment in the United States. It is published by the National Fire Protection Association, or NFPA, and is updated every 3 years to reflect the latest advancements in electrical technology and safety practices. The NEC is organized into chapters, articles, and sections, each addressing specific aspects of electrical installations. Chapter 1 covers general requirements such as definitions, scope, and administration. Chapter 2 deals with wiring and protection, including overcurrent protection, grounding, and bonding. Chapter 3 covers wiring methods and materials, as discussed earlier. Chapter 4 covers equipment for general use, such as receptacles, switches, and lighting fixtures. Chapter 5 covers special occupancies, such as hazardous locations, healthcare facilities, and swimming pools. Chapter 6 covers special equipment, such as electric signs, elevators, and electric vehicles. Chapter 7 covers special conditions, such as emergency systems, fire alarm systems, and communication systems. Chapter 8 covers communications systems such as telephone, data, and cable television systems. Chapter 9 contains tables and examples that are used to supplement the requirements in the other chapters. The NEC is not a law itself, but it is often adopted by state and local jurisdictions as part of their building codes. This means that compliance with the NEC is legally required in many areas. Even in areas where the NEC is not legally mandated, it is widely recognized as the standard of care for electrical installations. Adhering to the NEC helps to ensure the safety of people and property, and it can also reduce the risk of electrical fires and other hazards. When working on electrical installations, it is essential to have a thorough understanding of the NEC and to follow its requirements carefully. This includes using the correct wiring methods and materials, properly grounding and bonding the electrical system, and providing adequate overcurrent protection. It is also important to obtain the necessary permits and inspections to ensure that the installation complies with all applicable codes and regulations. In addition to the NEC, there are other standards and guidelines that may be relevant to electrical installations, such as those published by Underwriters Laboratories, or ALL, the Institute of Electrical and Electronics Engineers, or IEE, and the American National Standards Institute, or ANSI. These standards cover a wide range of topics, including product safety, electrical design, and testing procedures. It is important to be familiar with these standards and to follow them as appropriate. When selecting electrical equipment, it is important to choose products that are listed and labeled by a nationally recognized testing laboratory such as UL or ETL. Listing and labeling indicate that the products have been tested and certified to meet the applicable safety standards. It is also important to choose products that are appropriate for the intended application and that are compatible with the existing electrical system. When installing electrical equipment, it is important to follow the manufacturer's instructions carefully. This includes using the correct tools and techniques, properly connecting the equipment to the electrical system, and verifying that the equipment is functioning properly. It is also important to provide adequate ventilation for electrical equipment to prevent overheating. Finally, it is essential to maintain electrical systems properly to ensure their continued safe and reliable operation. This includes performing regular inspections, testing electrical components, and replacing worn or damaged equipment. It is also important to keep electrical panels and equipment rooms clean and free of obstructions. By following these guidelines, it is possible to create electrical systems that are safe, reliable, and efficient. The National Electrical Code provides specific guidelines for determining the appropriate ampacity, or current carrying capacity, of conductors. Ampacity is the maximum current, in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. The NEC provides ampacity tables that list the ampacity of various conductors based on their size, insulation type, and installation conditions. Table 310.15b16 in the NEC is commonly used to determine the ampacity of conductors in raceways or cables. This table lists the ampacity of conductors based on their size, insulation type, and the ambient temperature. The ampacity values in Table 310.15b16 are based on a maximum conductor temperature of 60 degrees Celsius, 75 degrees Celsius, or 90 degrees Celsius, depending on the insulation type. The ampacity of a conductor must be adjusted for ambient temperatures that are higher than the values listed in Table 310.15b16. The NEC provides adjustment factors that are used to reduce the ampacity of conductors based on the ambient temperature. The ampacity of a conductor must also be adjusted if there are more than 3 current-carrying conductors in a raceway or cable. The NEC provides adjustment factors that are used to reduce the ampacity of conductors based on the number of current-carrying conductors in a raceway or cable. The ampacity of a conductor must be selected to be equal to or greater than a non-continuous load plus 125% of the continuous load. A continuous load is a load that is expected to operate for 3 hours or more at a time. The non-continuous load is the load that is not expected to operate for 3 hours or more at a time. For example, if a circuit has a continuous load of 10 amps and a non-continuous load of 5 amps, the ampacity of the conductor must be at least 10 amps plus 1.25 times 5 amps, which equals 16.25 amps. Therefore, a conductor with an ampacity of 20 amps would be required. It is important to consult the NEC and other applicable standards to determine the appropriate ampacity of conductors for specific applications. Improperly sized conductors can overheat and cause fires. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect conductors from overcurrent. Overcurrent is any current that exceeds the ampacity of the conductor. Overcurrent protection devices are designed to trip or blow when the current exceeds a certain level, interrupting the circuit and preventing damage to the conductor. The NEC requires that overcurrent protection devices be sized to protect conductors from overcurrent. The overcurrent protection device must be sized to be no larger than the ampacity of the conductor. For example, if a conductor has an ampacity of 20 amps, the overcurrent protection device must be sized to be no larger than 20 amps. The NEC provides specific guidelines for sizing overcurrent protection devices for different types of circuits and equipment. It is important to consult the NEC and other applicable standards to determine the appropriate size of overcurrent protection devices for specific applications. Improperly sized overcurrent protection devices can fail to protect conductors from overcurrent and can cause fires. Grounding and bonding are essential for electrical safety. Grounding is the process of connecting electrical equipment to the earth. Bonding is the process of connecting different metal parts of an electrical system together. Grounding and bonding help to protect people from electric shock and to prevent electrical fires. The NEC requires that all electrical equipment be grounded and bonded properly. The grounding system must be designed to provide a low impedance path for fault current to flow back to the source. This allows the overcurrent protection device to trip or blow quickly, interrupting the circuit and preventing damage to the equipment. The bonding system must be designed to ensure that all metal parts of the electrical system are at the same potential. This prevents voltage differences from occurring between different metal parts, which can cause electric shock. The NEC provides specific guidelines for grounding and bonding electrical systems. It is important to consult the NEC and other applicable standards to ensure that electrical systems are grounded and bonded properly. Improperly grounded and bonded electrical systems can be dangerous and can cause electric shock and fires. The selection and installation of electrical cables in conduit and plenums require careful consideration of several factors, including the National Electrical Code, cable ratings, and environmental conditions. First and foremost, it is essential to consult the NEC and any applicable local codes to ensure compliance with all relevant regulations. The NEC provides detailed guidelines for wiring methods, conductor ampacity, overcurrent protection, grounding, and bonding. These guidelines are designed to ensure the safety of people and property and to prevent electrical fires and other hazards. When selecting electrical cables for installation in conduit, it is important to choose cables that are rated for the appropriate voltage, current, and temperature. The voltage rating of the cable must be equal to or greater than the voltage of the circuit. The current rating of the cable must be equal to or greater than the expected load in the circuit. The temperature rating of the cable must be suitable for the ambient temperature in which the cable will be installed. In addition to the NEC requirements, there are also specific requirements for cables installed in plenums. Plenums are spaces within a building that are used for the circulation of environmental air, such as heating, ventilation, and air conditioning, or HVAC, systems. Cables installed in plenums must be listed and labeled for plenum use. Plenum-rated cables are designed to have low smoke and flame characteristics, which helps to reduce the risk of smoke inhalation and fire propagation in the event of a fire. When installing electrical cables in conduit, it is important to follow the manufacturer's instructions carefully. This includes using the correct tools and techniques, properly supporting the conduit, and ensuring that the cables are not damaged during installation. It is also important to avoid overfilling the conduit, as this can make it difficult to pull the cables and can reduce their ampacity. When pulling electrical cables through conduit, it is important to use a cable lubricant to reduce friction and prevent damage to the cables. The lubricant should be compatible with the cable insulation and the conduit material. It is also important to avoid pulling the cables too tightly, as this can damage the insulation. After the cables have been pulled through the conduit, they should be properly terminated at the electrical equipment. This includes stripping the insulation from the ends of the conductors, crimping or soldering the conductors to the terminals, and tightening the terminals securely. It is also important to ensure that the conductors are properly identified and labeled. The NEC provides specific guidelines for identifying and labeling conductors. These guidelines are designed to help prevent accidental miswiring and to ensure that the electrical system can be easily maintained and repaired. Finally, it is important to inspect the electrical installation carefully after it is complete to ensure that it is safe and reliable. This includes checking the wiring connections, verifying the grounding and bonding, and testing the overcurrent protection devices. It is also important to document the electrical installation properly, including the wiring diagrams, the equipment specifications, and the test results. This documentation can be helpful for future maintenance and repairs. Always to energize circuits prior to working on them.